Hello and welcome to this video on metallic bonding. It has specification reference 3.1.3.3 and 3.1.3.4. In this lesson on metallic bonding, we're going to do the following. We're going to answer this question: what is the nature of metallic bonding? So as we know, that bonding is an electrostatic attraction. So if bonding is an electrostatic attraction between two charges, what in metallic bonding is positive and what in metallic bonding is negative? We'll see what makes a metallic bond like that, and we'll also have a look at what sort of structure metal atoms form. So we saw simple molecules, we saw giant covalent macromolecules, two different structures. We saw ionic crystals as well in structure. So we've seen three structures so far, and we're going to have a look at this fourth structure here. Then we'll move on to see how the bonding and structure determine various properties, such as melting points and conductivity of heat and electricity. So here on this slide, you can see we have a giant metallic lattice structure. I'm just going to write that out. So it's a giant because there's billions and billions of atoms in one structure. It's metallic because the element is a metal, and it's a lattice because it is regular. So you see there are rows here of, in this case, magnesium ions, and these rows repeat each other and they are on top of other rows, and so the regular nature means that it's called a lattice. And so that's what we're looking at here, and what we can also see is we've got some delocalized electrons. So all of these electrons, E- signs here and everywhere else, these are our delocalized electrons. And in a metal, it's the outer electrons that become delocalized. So here we've got magnesium as the example. You know that magnesium is in group 2, which means it's got two outer electrons. And so it's those two outer electrons that become delocalized when it's in metallic form. And when we say delocalized, what we mean is that the electrons are not attached to a single atom or ion. They can move freely, so in one instant they'll be closest to one ion and they'll be moving around, and so in another instance they'll be closest to another ion and they are free to move. So if magnesium's two outer electrons are delocalized, then what is left is actually no longer an atom, it's an ion. And if it's lost two electrons, it's going to have a 2+ charge. So what we say is that the metal ions are surrounded by a sea of delocalized electrons. So the metal ions here are surrounded by this sea of delocalized electrons. And what else we can say is that the metallic bond is the attraction between the sea of electrons, which are negative, and the positive metal ions. So you're going to have temporary but strong bonds between the moving electrons and the static ions. So you're going to have billions of these little tiny electrostatic attractions between the sea of electrons and the positive metal ions, and that becomes the metallic bond. And it's quite strong. As you know, most metals are solid at room temperature with melting points up to, in the case of tungsten, up to about 3,400 degrees Celsius. Okay, so that is the first point we want to make, and we're going to summarize that point by saying that metal elements exist as giant metallic lattice structures. So I've mentioned that these electrostatic attractions, these metallic bonds, are quite strong, and so these are the bonds that hold all the magnesium particles together in a solid structure. And so these would be the bonds, therefore, that are broken when the metal melts. And so if they are strong, they should have high melting points. So we're going to go and discuss the melting points of metals now. And on the left here we've got sodium, and as you know, sodium is in group 1. So that's going to have 1 outer electron, and magnesium is in group 2, so that's going to be 2 outer electrons. And what that means is that the bonding in the sodium, the metallic bonding in the sodium, is slightly weaker than the bonding in magnesium, because we've only got a 1+ ion, and the sea of electrons is only 1 electron per atom. Whereas in magnesium we've got a 2+ ion, so a higher positive charge, and we've got twice as many electrons in the sea of delocalized electrons. So that will make a higher force. Right, so I'll draw it with more hatch lines than with sodium. So the bonds would be slightly weaker in sodium than in magnesium, and that shows up in the melting points. So the melting point of sodium is 98 degrees C, whereas the melting point of magnesium is 649 degrees C. So it makes quite a bit of difference there. And indeed, if you went to aluminium, so aluminium, you remember, is in group 3, so the metal ions in the aluminium structure would be 3+, and you'd have 3 delocalized electrons for every atom of aluminium, and so the bonds would be stronger as well. And indeed, the melting point of aluminium is about 660 degrees C. Okay, so what I've done is I've given you already one reason why the melting points of metals increase as the charge on the ion increases, but there's another reason as well, and that is the size of the ion. So in the case of sodium compared to magnesium, sodium is actually the larger ion, and magnesium is the smaller ion, because the electrons are held a bit closer to the nucleus as you go along a period. And indeed, aluminium is smaller still, for the same reason. So that's the second reason why the melting points increase as you go from sodium to magnesium, and you go from magnesium to aluminium. They get smaller, and therefore they're more closely packed, and therefore the electrostatic attraction can hold the particles together more strongly. And consequently, of course, you would then need more energy to break those stronger electrostatic attractions. Okay, so that increases right the way up to transition metals. So you'll be familiar with transition metals having much higher melting points than even 660 of aluminium, and indeed the metal that has the highest melting point is tungsten, and tungsten has a melting point of about 6,300 Celsius, which is very high, and indeed just about as high as the allotropes of carbon. So when carbon forms graphite and diamond, they don't really melt, they sublime, but they sublime at about 6,400 degrees C. And so we can summarize the point of this slide with the title here. So we're saying that metals have high melting points because of the strong electrostatic attraction between the positive metal ions and the delocalized sea of electrons. So they'd be the negative, and obviously the metal ions are positive. So another point about the structure of metals is that the layers of metal ions can slide over each other when you pull the metal, for example. So as we know, we can pull metals into wires, and we can bend them into all sorts of shapes to make car bodies out of them, for example. And that is because of the following. Okay, if we look at this diagram of the sodium lattice, you can see that the ions are arranged in very regular layers. But the important point is that the bonds between the ions and the electrons are all transient. All right, so as the electron moves, let's take this electron here, and at one instant it's got a bond to, let's say, these two ions, but then in the next instant it's moved over here, right, and it will have a bond to these ions. So the bonds are very transient. So if you applied a force, you could easily move the layer over the underneath layer, and the bonds would reform straight away. So there's no strong bond breaking and bond making process going on, which allows one layer of metal ions to slip over the underneath layer of metal ions. Whereas if you were to do that in an ionic crystal, there's very fixed bonds between the ions. So the one cation is electrostatically attracted, so making an ionic bond with the anion that's next to it, and the other anions that is next to it. And none of these ions are moving, and the electrons are all in fixed positions, or at least fixed, connected to a particular ion, and they're not delocalized like the delocalized electrons in a metal. And so when you apply the similar sort of force to a ionic substance, first of all, nothing will happen until the force is strong enough, and then the whole thing will shatter. So coming back to metals, the result of this is, of course, that we can make things like wire, and because they can be, this copper wire here might have started off as an ingot that got gradually stretched and stretched and stretched until it was a very thin wire, and it's still not breaking because the metal particles are very happy slipping over each other. But before we move on, let's just remind ourselves of a couple of words, one of which is ductile. And this is ductile. Ductile is being able to be stretched into a wire. And the other similar word is, similar property anyway, is malleable. And malleable is the ability to be shaped. So, for example, a car body starts out as a flat metal sheet, and that will be bent into the shape that's required. Also, you're making a metal pan. Start out as a flat metal sheet, and it will get quite easily get pressed into the shape of the pan. So malleable and ductile, two interesting words for this little topic here. So we move on now to talk about conductivity. And what we mean is we mean electrical conductivity firstly, and then also thermal conductivity. So dealing with electrical conductivity first, let's have a look at this chart. And so we have conductivity here. It's just relative conductivity, and it would be silver is the gold standard, forgive the pun. Silver is the gold standard, so that's given a conductivity of 1, and then all the other metals are compared to silver. And you can see, of course, that copper is a very good conductor of electricity, which is why it's used in all our electrical wiring, because it's nearly as good a conductor as silver, but is a lot cheaper than silver. Now, aluminium is a lot cheaper than copper, in fact, but the problem with aluminium and its conductivity is that it's a bit more reactive, and so it forms a coating of aluminium oxide on the outside of the aluminium, which the aluminium oxide doesn't conduct electricity, so that could be a problem. But it's still used, aluminium is used to conduct electricity in pylon wires, because it's lighter than copper primarily, while still being a good conductor of electricity. And it's quite cheap as well, because you need a lot of cable to stretch across the country to get from the grid to all of our houses. Now, what you can see here is you can see the best conductors of electricity are copper and silver, and one of the reasons for that is that the transition metals, many of the transition metals, as well as their sea of electrons containing their outer electrons, also their 3D electrons are donated to the sea. Right, so you've got quite a high number of electrons per ion in the sea, and consequently a high charge on the ions. So that means that the conductivity is good. Also means that the melting point is going to be higher, because you've got highly charged ions and lots of electrons in the sea of electrons. So you're going to have strong electrostatic attraction and therefore strong metallic bonds. And so there you have the conductivity of electricity. So moving on to the conductivity of heat. And we can see a chart here where, again, we've got copper at the top. It's a very strong conductor of heat, also iron and steel. But down here, we've got our non-metals, and these are effectively insulators that don't conduct heat. Styrofoam that you might make your coffee cups out of, for example. So we can see data there suggesting that metals are good conductors also of heat. And it's for the same reason. The reason why metals can conduct both electricity and heat very well is because of the sea of electrons, which carry either the electricity or the energy, i.e. the heat. So let's just remind ourselves of this sea of electricity. So let's say we apply a potential difference to this sample of magnesium. So on the left there is a positive charge, on the right there is the negative charge. So what you're going to get is you're going to get all these electrons moving away from the negative charge and making their way towards the positive charge. And because they're mobile, they carry that electricity quite quickly, and that's what makes the metals good electrical conductors. And also you could apply heat. So let's draw a little flame here. So you could apply heat to one side of the metal, and that would quickly energize this electron here, which I've drawn in red, and it's going to have a lot more energy, so it's going to be a lot more mobile, and it's also moving around, so it's going to diffuse in the way that a pollen particle also diffuses, and so it's going to make its way through the lattice structure as well, carrying heat with it. Whereas with an insulator, it's just the atomic particles that when they're heated, they vibrate a bit more, and the vibration transmits the energy to the next particle, which then becomes a little bit hotter and vibrates, but a bit less, etc., as you go along the material. And I think you can see that the electrons could carry the heat quicker because they're actually diffusing and physically moving, whereas if you're relying on the vibration of static particles, which can't move, that's going to be a lot slower, so the thermal conductivity will be lower. Okay, so just to summarize, the reason why metals are good electrical and thermal conductors is that the mobile sea of electrons can carry either the charge for electrical conductivity or the heat for thermal conductivity. So our last point here is made using this picture here. It's a picture of several metal pipes, and these metal pipes might carry water, for example. And if they are carrying water, of course the thing that you don't want is you don't want the metal to dissolve in the water. So the final point is this: metals are insoluble, so the metal themselves won't dissolve in water, and they don't dissolve in many things apart from other liquid metals. And the reason for that is that the strong metallic bonds require too much energy to break up the lattice, and the water molecules are not polar enough to do that and don't form stable enough bonds with the metal ions in order to make that thermodynamically acceptable. So there you have it. That's the last point. Metals are insoluble except in liquid metals because of the strength of the metallic bonds. And that just leaves us to review our learning objectives to make sure that we've covered it all off. First of all, we asked ourselves what's the nature of metallic bonding, and so the main points there, we have metal ions. All right, so I'm just going to use M for metal. So you have metal ions, positive metal ions, making an electrostatic attraction to a sea of mobile electrons, and that is metallic bond. And they form a giant metallic lattice because it's unending and it is regular patterned. So that's why we call it a lattice, and it's a metal, so we call it a metal lattice. So that's the first two covered off, and then last point, how do they determine the properties such as melting points? Well, the bonds, these metallic bonds, are strong, and so the melting points are high, and they are higher with metal ions that have a higher charge and are smaller. So let's just remind ourselves there, we've got higher with higher charged ions and smaller size, so higher charge density. And the conductivity that we've just done, conductivity of heat and electricity, both facilitated by the mobile sea of electrons. So there we have metallic bonding and the properties of metallic structures. Hope that's been clear.